Okay, so just to recall what we have discussed earlier, we have defined there are some non-zero vectors. There exist some non-zero vectors. Not all vectors are eigenvectors. For example, x that is x not equals to 0 and some real numbers, real or complex numbers. Okay. For a given matrix A, for a given square matrix, we are not telling whether this matrix is invertible or not. We are just writing square matrix. Ax for a given square matrix A, n by n or m by n order, if we have Ax equals to lambda x, this equation satisfied, then we call lambda is an eigenvalue of A and x is the eigenvector. X is corresponding eigenvector. Related to lambda. Okay, they come together. If you talk about eigenvalue, then you have to talk about eigenvectors also. You cannot say that lambda is an eigenvector of alpha. That means you are also telling it is hidden that there exists some x. You are talking also about the x. For that, ax equals to lambda x. This is satisfied. So if you just quickly think about example 2 that was I have included there, we have seen that if we have a 3 by 3 matrix, then we will have 3 eigenvalues. Okay. Now question is how many eigenvectors we will have. So this is related to lambda 1 equals to 0, lambda equals to 3 eigenvector. So this is eigenvector. This for this eigenvalue we have obtained this eigenvector, and for lambda 3 equals to minus 4, we have received this eigenvector. Now what will happen if we have x is a non-zero vector and I is a 3 by 3 matrix, for example 1 0 0 0 1 0 0 0 1, or if you have 1 0 0 1. Okay, if you multiply with any vector, what you will get? You will get the same vector, right? Yeah, right. So what happens if you just multiply with a non-zero vector? So any non-zero vector, remark, any non-zero vector is an eigenvector of identity matrix of order n by n and corresponding to the eigenvalue for lambda equals to 1. Because what we can write, we have seen Ax equals to lambda x. But if we replace this A matrix with identity matrix, then what we see? We see Ix equals to always x. So here 1 times x you can write. So lambda equals to 1. Okay. So any non-zero vector can be treated as an eigenvector of this identity matrix. Okay. Now think about what will happen if A is a zero matrix. Then what will be the eigenvalues? Tell me. And eigenvectors. Anyone can respond? In this case, actually everything will be trivial. Every equation will be satisfied, right? 0 into 0 something will be 0. So this is a very eigenvalue will be infinite. No. I am talking about what is eigenvalue. Now, not number of eigenvalues.
0.
About, yeah. So if you write this 0 times x, lambda times x, so that is not possible. So 0 into, because x is non-zero, so left hand side will be always non-zero. 0 times some 0 matrix into non-zero vector, so it will be 0. Okay, and 0 is also this is since x is non-zero, so this lambda will always be 0. So in this case, 0 is the only eigenvalue if we have 0 matrix. Okay, right. Now we try to look at this picture. So this is a 3 by 3 matrix. We have 3 eigenvectors. Eigenvalues. Depending on that, we have seen that we can get 3 eigenvectors. Now there is a natural question. If we have n by n matrix, the question is how many eigenvalues can be there? Okay, the answer will be n. Can the eigenvalues be repeated? Okay, the answer will be yes. Okay, because if you look at 1, 0, 0, 0, 1, 0, and 0, 0, 1, it has eigenvalues are lambda 1, lambda 2, and lambda 3 are 1. They are repeated, but it will have 3 eigenvalues. Because if you try to find the I times minus lambda times I and take the determinant as 0. So you will get here 1 minus lambda 0, 0, 0, 1 minus lambda 0, 0, 0, 1 minus lambda. So that's our characteristic equation, and this will give you lambda minus 1 all cube equals to 0. So this will give you lambda equals to 1, 1, 1. Okay, so yes, eigenvalues can be repeated. Now, if these eigenvalues are repeated, we have seen in the previously that if we have 3 eigenvector values, then we can have 3 eigenvectors. Now the question remains, corresponding to a particular eigenvalue, how many eigenvectors are there? Right? How many eigenvectors can be there? Not only that, the next question says that how many linearly independent eigenvectors can be there? Okay. So all these answers will answer to this question with some examples. So first example, let us take, this is a 2 by 2 matrix. Okay. This is a 2 by 2 matrix. And then we try to find out the characteristic equation. Characteristic equation is determinant of A minus lambda I, we make it 0. So here lambda equals to 5, 5. Okay, so this eigenvalues are repeated here. Now the question is how to find the eigenvectors. So how many eigenvectors will be there? Because just now we have seen this is a 3 by 3 matrix. It has 3 eigenvectors. So it is a natural question that if we have a 2 by 2 matrix, so we want at least 2 eigenvectors. Okay, this can be our question. So the answer is actually no. It is not necessary to have n different eigenvectors. Sorry, n linearly independent. Because I will tell you why. So here, if you try to solve to find out the eigenvector, so you have to make it A minus lambda I. Lambda is 5. So lambda I, make it 0, take the determinant and solve it and try to find out the eigenvector. So this is a system of linearly augmented matrix and then try to find. You don't need to do the Gauss-Jordan elimination because this is a 2 by 2 system. So directly we can here. So this is one eigenvector. Vector. That means if you multiply 3, 4, minus 1, 7, here you can multiply 2 and 1, then you will get 5 times 2 and 1. Okay. The meaning of eigenvalue and eigenvector is this one. So this is an eigenvector. So this corresponding to lambda equals to 5, we will have this situation. Now, if you just in place of 2 and 1, if you write here 4 and 2, then you will get 5 times 4 and 2. Not only that, if you just multiply again 8 and 4, then you will get here 8 and 4. Try to verify what I am writing, they will be correct. So what it means that we may have eigenvectors, all these are eigen. Suppose this is x. X can be 2, 2, 1. Okay. It can be 4, 2. It can be 8, 4. Whatever you take, it can be 16, 8, and so on. So there will be infinite number of possibilities. But what are they? They are linearly dependent because the second vector, if you multiply with 2, then you will get the second vector. So that means they are not linearly independent. So here only one vector is linearly independent. So that is why corresponding to this lambda equals to 5, we have only one linearly independent eigenvector here in this case. So although this matrix is 2 by 2 matrix, 2 by 2 order, and it has a repeated eigenvalue, for that we get only one eigenvector, linearly independent, single eigenvector. Because this can be represented, all these values are actually can be represented by this one. There may be infinite number of choice for eigenvectors, but for linearly independent vectors, you will have only one vector. Now, if you look at whether it is always the case, that if we have the multiplicity of this order of this factor, suppose lambda equal lambda minus 5 whole square, if it is power is 2, then we will always have only one vector. The answer is no. Sometimes we may have two vectors also. So that will be given in the next example. For example, if you take this example, here we have lambda equals to 11, lambda 1 equals to 11, and lambda 2 and lambda 3 are repeated. So this is 8. So this is multiplicity. Multiplicity of 8 in this characteristic equation is 2. Multiplicity of 8 is 2. Okay, so multiplicity is of 11. Multiplicity of 11 is 1 here. Because this factor has only one power. It has two power. So we call it a multiplicity. Okay. Now, as usual, if you try to find out the eigenvector corresponding to this eigenvalue, so then you will have this system of linear equation and try to solve it. You will get another one vector. So this is one eigenvector. Let us call it a first eigenvector. Then we try to find out for lambda equals to 2, lambda and lambda 3. Both are equal. So for 8, we will again take the augmented matrix and then try to solve. After row operations, we can see that this system is reduced to only one equation. So since only one equation, so here it is a pivot element, you can write it. Or you can write it a pivot element. So that means one basic variable, this is x1, and the other two are non-basic. There is free variable, x2 and x3 are free variables. Okay. So that is why what we can say, if we choose k2 and k3 equals to 1, 0, even you can think 1, 1 also. In that case, what we have actually k1 plus k2 plus k3, this becomes 0. So this is 1. If you think this is also 1, so you will have k1 equals to minus 2. So in that case, the eigenvector can be minus 2, 1, 1. This is one example. Or you can also have of this form, k1, okay, so k1 plus k2 plus k3 equals to 0. So you are free to choose this k2 and k3 value. Suppose you choose 1 and 2. This is 1, this is 2. So this will become the x vector, that eigenvector will become now. In that case, this eigenvector, let us call it eigenvector, EV. EV is this one. So here it will be, k1 will be minus 3, 1 and 2 of this form. For different choice of this, so but you will have this situation that only two independent vectors will be there, linear. Only two linearly independent eigenvectors will be there. It may be you will have infinite choice, like I have seen, like we have seen here, that we may have infinite choice, but linearly independent only one vector here. So similarly here, we'll have only two linearly independent vectors. So what it means, if the multiplicity is 2, it can have at most two linearly independent eigenvectors. Maybe there. So these are some important observations for this case, eigenvalues and eigenvectors. Now there are some properties of eigenvectors and
Sir,
eigenvalues.
what are those two linearly independent eigenvectors, sir, in that one? We can choose any two,
Okay.
sir, or else
Yeah,
only
you can.
K2 and K3.
So what happens? Yeah, the question is how to choose these linearly eigenvectors, linearly independent eigenvectors. So if you choose 1, 2, 3, 4 also, you can have, because you are free to choose, okay. So you can choose any values. But what happens if you choose 0 and 1, then it will be easily understandable. Otherwise, you may not be able to find out that which vectors are actually linearly independent, because there are infinite number of choices. Okay, so that is why it is always recommended, you can, if you have two free variables, choose one as non-zero, another is zero. Similarly, first one will be zero and the other will be non-zero. So this k1, sorry, this k3 and this k2, these two are linearly independent vectors now in this case. Because if you try to multiply this one, okay, you cannot write k2 in terms of k3. If you remember the linearly dependent definition, if they are dependent, then you can write one vector in terms of the other vector. Right?
Sir, we have 4, means plus K4 also is there. Then we have to choose 2 zeros and 1 1, or only 1 0 and 2 1.
So you're talking about if we have k4.
Yes, sir.
Tell me k4, what is it?
Means it is also a free variable like 2 and 3.
No, in that case, the matrix will be 4 by 4 matrix, right?
Yes, sir.
Yeah. Depending on the situation, you have to find out what can be the eigenvectors and eigenvalues. See, eigenvalues, finding eigenvalues is very easy. Just find the characteristic equation and solve it. The tricky part is to find out how many eigenvectors are there. Okay, so for that you have to look at the multiplicity of the eigenvalue. Here the eigenvalue, the multiplicity is 2 here. So it can have maximum 2 eigenvalues in linearly independent eigenvectors. Sorry, not values, eigenvectors. In the earlier example, we have seen this is a 2 by 2 matrix, but we can have only one eigenvalue. Sorry, eigenvector linearly independent in this case. Because the system has reduced in such a way that we are getting only one solution. There are only k1 equals to 2 times k2. So that's the relation between these
Sir,
components of the eigenvector. It is the
sir,
only relation.
sir,
So that is, yes, tell me.
for lambda is equal to 11, we had find eigenvectors, na, sir.
Yes.
For that, if we take K3 is equal to 0, then K1 is all zeros, na, sir. 0, 0, 0.
Here it is.
For lambda is equal to 11, sir.
Yeah, lambda equals to 11.
If we take K3 is equal to 0, then K1 is equal to 0, 0, 0, na, sir.
No. See here, what will be the system now? Here the system will be x1 minus x2. Will be here two basic variables. Here we will have two basic variables. Only one free variable, x3 is free. Right? So that is why I have mentioned that you have to understand which are the basic variables and which are the free variable.
Sir, for free variables, we
So this
shouldn't
system
take
becomes
0, sir.
yeah.
Sir, for free variables, we shouldn't take 0, sir. Value assigned to be.
You can take 0 also, no problem.
Sir,
So
then
this system is reduced to like this only. x1 minus x3 equals to 0. x2 minus x3 equals to 0. Okay.
sir, when we
So
keep
what we
x3
get?
as 0.
x1, x2, and x3. Okay. All are equal
Yes, sir.
by this system.
Yes, sir.
Okay. Now you are telling that 0, you can take 0, 0, 0. Right? Can
Yes,
we
sir.
take this? The
Yes,
answer
sir.
is no, because this is eigenvector. Eigenvector cannot be zero vector. It has to be non-zero vector.
Okay, sir. Or else we can take k3 is equal to -1, sir.
Yeah, -1 is also okay. -1, -1.
Other than except 0, 0, 0, we can take anything, sir. Is it, sir?
Yes, we have to take a non-zero vector. The choice of these components, okay, these components will be in such a way that the resultant vector should not be a zero vector. Otherwise, it will contradict the definition of eigenvector.
Okay, sir.
Got it? You are free to choose anything, but not a zero vector for eigenvector. You are free to choose this is -2, -2, then -2. Anything you can choose, but you should not, your choice should be in such a way that the resultant eigenvector should not be a zero vector. Otherwise, it will contradict the definition of a eigenvector. Okay. If you remember the definition of eigenvector, it is a non-zero vector. Eigenvector should be non-zero vector. But there are some important properties that are actually we'll just mention them without proof. Proof are not part of our syllabus, but these results are very important to find out some important some other interesting results also. Any square matrix, it says, if you have a lambda 1, lambda 2, lambda n, then if you take A transpose, the eigenvalues are also A transpose will always be same. A transpose and A will have same eigenvalues. Now, if you try to verify this result, take this simple example, 3, 4 and -1, 7. -1, 7. So that is our A matrix. What will be A transpose? A transpose will be 3, 4, -1, 7. So if you take A minus lambda I equals to 0, then you will get here 3 minus lambda -1, 4, 7 minus lambda equals to 0. And if you just simplify it, so you will get here it as 21 minus 3 lambda minus 7 lambda minus what is it, lambda square, so plus lambda square minus plus 5. So this will become 21, sorry, this is 4, not 5, 4. Yeah, so 21 plus 4 plus 21, so this is 25. And then here we have -3 lambda, 7 lambda, so this is 10 lambda plus lambda square equals to 0. We are making it 0. So here it is nothing but lambda minus 5 whole square equals to 0. So lambda equals to 5, 5. So A matrix has the lambda values are actually 5, 5. So A transpose will also have the same eigenvalues. Now, if you the trace of a matrix, it says if a given matrix is written as this form: A11, A12, A1n, A22, sorry, A21, A22, A2n, AN, N1, AN2, ANN, for a square matrix. Okay. Because we are talking about the eigenvectors, eigenvalues, so it will be one square matrix, and for that trace, for this is A is a trace. We call this is as trace of A, which is denoted by triar A, which is the summation of A11 plus A22, the main diagonal elements, ANN, or you can write summation AII, I equals to 1 to n. So if you take the diagonal sum of the diagonal elements, then we call this term as a trace. And the next theorem, it says the sum of the eigenvalues of a matrix is equal to the trace of the matrix. If you just look at the matrix, A equals to 3, 4, and then we have seen -1, 7. Just now we have seen it has lambda minus 5 whole square equals to 0. The characteristic equation. Okay. Then lambda equals to lambda 1 equals to 5, and lambda 2 is also 5. The trace of A is actually 3 plus 7. You can write it as of this A11 plus A22. So here it is 3 plus 7. But lambda 2 is equal to 5 plus 5. So this is 10. 5 plus 5 is also 10. So this result is also verified. In fact, there is actually mathematical proofs are there, but we don't have the proofs in this course. So that I am giving one simple examples to understand this idea. Now, if you try to find out the determinant of A, what is it? 21 minus 4. So this becomes 25. Now there is another theorem that product of this lambda 1 times lambda 2 is equal to the determinant of A. Here it is 25. So 5 times 5 is 25. This is another result. So from here we can just write it. This is lambda 1 plus lambda 2 lambda n. Whether it is repeated or not, we will write as n eigenvectors. Okay. Sum of eigenvectors, eigenvalues. So trace, there is a sum of the diagonal elements is equal to the sum of the eigenvalues for a given square matrix. Now the determinant of that square matrix is equal to the product of the eigenvalues. Now if you try to verify some other, the product of the eigenvalues of the matrix. Now if you just try to look at this, this example, here it is. 1, 2, minus 1, sorry, 1, 2, 1, minus 6, minus 1, 0, minus 1, minus 2, minus 1, 2, 1, 6, minus 2, 0, minus 1, minus 2, minus 1. So this is a given matrix A. Okay. Okay, right. So this lambda 1 is 0. Lambda 2 is, what was that? 3 and minus 4. Okay. So if you take the product will be 0. Lambda 1, lambda 2, and lambda 3. This sum will be 0. If you take the product is 0 actually. Let us take the lambda 1 plus lambda 2 plus lambda 3. What is it? So 0 plus 3, 3, and minus 4 is minus 1. If you take this, somehow it is minus 3 plus. This was supposed to be trace. Trace A is equals to sum of lambda 1, lambda 2, lambda 3. Okay. 0 plus 3 plus minus 4. This is going to be minus 1. And if you take from this matrix, so this is 1 plus minus 2, then plus again minus 1. So yeah. Maybe I have written wrongly, but these theorems are correct actually. 1, 2, sorry, this is minus 1. Somebody should tell me that this is minus 1. This is minus 1. Okay. So this is minus 1, minus 1. These theorems are universally true. It cannot be wrong for any particular example. Okay. Otherwise, we may have some done mistake while writing the matrix. So if you try to find out this 1 plus 1, so this is again minus 1. So trace formula verified. Now if you try to find out the determinant of this matrix, what it will be? 1 times, so minus of minus plus 1 minus 0, then minus 2 times. Okay, so this is minus 6 minus of 0, then plus 1 times. Okay, so this is gone. So minus 12 minus of minus, this becomes plus. Again, this minus is 1. So if you try to look at here, it is 1 minus of minus 2 into minus 6. So this becomes 12. Then plus 1 into minus 12. So this becomes minus 12. And then this is 1 into minus 1. So this is 1. Okay, so this one will get cancelled. This minus 12, this minus 12 gets cancelled. So this is 0. Yeah. So determinant of A, here also we get is 0. And by the formula of lambda 1, lambda 2, and lambda 3, multiplication of these 3 eigenvalues is also 0. 0 times 3 times minus 4. So again it is 0. So this formula is also verified. Okay. Now if we have eigenvalues lambda 1, lambda 2, and lambda n for a particular given matrix A, then the following results will hold. What are the results? If you multiply k times a, then the lambda values, the eigenvalues will be k times lambda 1, k times lambda 2, and k times lambda n. If you take the power a to the power m, then the eigenvalues will be lambda 1 to the power m, lambda 2 to the power m, and lambda n to the power m. For inverse, if you take the inverse, okay, the lambda values will be get inversed. That means 1 by lambda will be the eigenvalue corresponding to the inverse matrix of the given matrix. Similarly, for 1 by lambda 2 and 1 by lambda n will be the eigenvalues of the inverse matrix of the given matrix. Okay, so these properties are very important properties. Okay, now if you try to find out is lambda 1, lambda 2, and lambda n are given eigenvalues of n. The task is to find out the eigenvalues of the matrix A minus lambda I square.
So once can you go to the previous slide? I mean, just once.
This one?
Yes, sir. 1 second. I'm calling.
I'll be sharing all the PDF. No need
Yes, sir.
to-
Okay, sir. Done, sir.
Okay. So if you try to write, just write it a minus lambda I whole square. So you write it a minus lambda I times a minus lambda I. So here you will get a square minus a times minus lambda ai, right? So we can remove I. And then because I is an identity matrix, it will act like 1. So this is minus lambda a and then plus lambda I square. Again, it will be nothing but lambda I, lambda square into I times I is I. So this is nothing but a square minus 2 lambda a times so plus lambda square I. What we have just now seen, the eigenvector of a will be lambda 1 square, lambda 2 square, then dot lambda n square. For this one, lambda times a. So for this matrix, what will have the eigenvalues? Lambda into lambda 1 square, lambda into lambda 2 square, dot lambda into lambda n square. And for this one, what will have? It's nothing but just lambda square. Okay. So what we'll have is, because this is a negative sign is there, so this is lambda square plus again here it is lambda square will be there. I times I matrix is there, so here will also be lambda square. So you can see here now, but we have a multiplication by minus 2, so we'll have minus 2. So this will become lambda 1 minus lambda whole square. This will give you lambda 2 minus lambda whole square. So this is lambda n minus lambda whole square. So the eigenvalues of this matrix of a minus lambda I whole square are nothing but this dot. So that's how we can find out one given these are the given data. These are eigenvalues of the particular matrix. Our task is to find out the eigenvalues of this matrix. So we can just use some arithmetic formula or just matrix algebra.
Sir.
Yes.
Sir, is lambda a constant?
Yeah,
In this
here it is
case.
constant.
So,
Here it is constant. This lambda is constant here.
so in the second term, the eigenvalue for A will be lambda 1 only, na? Not lambda square.
Yeah, right. I made a mistake. Yeah, right.
Okay, sir.
Thank you for observation. Okay. Yeah. Just use these formulas and you will get the results. Okay. Now there is another important theorem. Okay, these properties I have already discussed. So I would recommend to verify, study and verify. Verify. Try to verify the results. I have included all these results here. So somehow I have discussed already. So I am just skipping this portion. Otherwise, we won't be able to complete our syllabus. Okay, the proofs are actually not needed. You just need to understand the statement. Proofs are not part of our syllabus. Of course, I mean, if you're interested, you can go through. I'm not discouraging in that. If you have problem, okay, you can discuss with me. Yeah. The thing is, we have to discuss the Cayley-Hamilton theorem. So that's a very important theorem for as an application, or you can call it a important application of eigenvalue and characteristic equation. So this theorem says if we have a square matrix, a square matrix is given, then that particular matrix will satisfy its characteristic equation. So if we have a characteristic equation of this form, then in place of lambda, if we substitute a, so a to the power n, a to the power n minus 1, last order of this form, and this k times I will be equals to 0. So this means it is satisfying the characteristic equation. Okay. So every square matrix, it satisfies its own characteristic equation. So if you just, for a simple example, if you try to find out a equals to, like we have seen, 3, 4, minus 1, 7. Its characteristic equation we have seen a lambda minus 5 whole square equals to 0. So if you try to put in place of lambda, put a minus, if you write here 5, so this would be invalid statement because we are writing one matrix. So 5 times we have to write I. If you write this is supposed to be 0. So if you let us verify whether it is true or not. So if you try to find out a minus 5i, what it is? So minus 3, 4, minus 1, 7, minus 5 times I. So that means you have to write 1, 0, 0, 1. So 3 minus 5, so 4, and then minus 1, 7 minus 5. Okay, so here it is minus 2, 4, minus 1, minus 2. Sorry, not minus 2, this is plus 2. Our aim is to show this square equals to 0. So let us take this square. So the square means we have to multiply again. So minus 2 a minus 5i whole square. Minus 2, 4, then minus 1, 2. Okay. So let us verify whether it is 0 or not. So minus 2 minus, so this is plus 4. Then 4 minus 1 into 4 into minus 1. So this is minus 4. Then 4 times minus 2, minus 8. So 2 times 4, so that is plus 8. So 1 time minus 1 into minus 2. So this is 2. So 2 into minus 1, so minus 2. Again 4 into minus 1, so minus 4. So 2 into again 2, so this is plus 4. So you will get here, this is 0, 0, 0, 0. So that means we are getting 0, 0, 0, 0. Okay, so this Cayley-Hamilton theorem is verified here for this particular example. Okay, now this Cayley-Hamilton theorem, because it satisfies the characteristic equation, so from there we have this relation satisfied. Now if you multiply, then it is actually helpful to find out the inverse. Okay, so we'll see one bigger example. So 3 by 3 order. Okay, now we have to apply. First, we have to show that it satisfies the characteristic equation. Then we have to find the inverse. So 3 tasks here. One, satisfy the find the characteristic equation. Okay, verify Cayley-Hamilton theorem. Second task is to find A inverse. And third task is to express this quantity in terms of a linear polynomial. So what is a linear polynomial? So that means a linear polynomial is of this form, x plus 1 is a linear polynomial. If you write x square plus x plus 1, then it becomes quadratic polynomial. The degree is 2 here. So linear polynomial means a polynomial in A. That means you want to write this expression in terms of this A plus some constant times I of this form, linear polynomial. So these are the 3 tasks we have to perform for this particular example. Now what we have, so a given matrix, try to find the characteristic equation. Let us do this. Let us simplify it. So finally, we have this characteristic equation of this form. So by Cayley-Hamilton theorem, it says it will satisfy this equation. So that means in place of lambda, if we put A, then it will satisfy. Okay. We are supposed to get the right hand side as 0 matrix. So for that, what we have to find? A is given. I, we know it is 3 by 3 matrix, identity matrix. We have to find A square. And then we have to find AQ. If we find all these things and then we do the arithmetic, matrix algebra, addition and subtraction, then we are supposed to get a 0 matrix. So let us verify. So you can compute, I will tell, to verify. There may be some misprinting, so you have to verify these things. So verify these results, A square. After finding A square, you can find AQ. Again, I will write to verify. Once you verify, the idea will be more clear to you. So the next task is to show that this is a 0 matrix. So this is up to the first task, that we have verified the Cayley-Hamilton theorem for this particular matrix, that it is satisfying its characteristic equation. The next task is to find the A inverse. So for A inverse, we have seen already that there is a formula. So from this equation, if you multiply with minus A inverse, then it will become of this form. 4 times A inverse equals to A square minus 6A plus 9I. So we already have calculated A square, A and I. The unknown part is now A inverse. So just substitute these values and just simplify. Then you will get A inverse of this form. So this is second task is complete. Now the third task is to represent this quantity in terms of linear polynomial. So what is a polynomial? The polynomial is of the form, if fx has the polynomial, is actually x to the power n plus x to the power n minus 1 or a times an xn. A polynomial is of this form, an minus 1 x to the power n minus 1 plus dot 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 h0. So for linear polynomial, we will have only a1 x1 plus a0 for linear polynomial. Now a linear polynomial, this is in x, polynomial in x. Now polynomial in a, that means we will have of this form. Because if you look at the other part, by Cayley-Hamilton theorem, this is 0. Again, this is part is 0 by Cayley-Hamilton theorem. So we'll have only this part remaining. So which is a linear polynomial in A. So our third task is also complete. Now these are for your practice problems. Try to verify these results. Okay. And let me tell you this part in the next class. That in fact, I can show you that every day we actually use the concept of linear algebra. If you do this Google search or some other internet search also, we are actually this event can be explained in terms of eigenvalue and eigenvectors also. We can explain it in terms of eigenvalues and eigenvectors. So I'll keep that particular example for the next class discussion. Okay, if you have any doubt, you can ask me.